Okay. All right, so I will do a brief summary of the things we've learned.
Mm-hmm.
I have the slide here, actually.
Lessons learned.
The lessons learned. There's one slide on the last slideshow thing that like summarizes essentially I think everything you're supposed to know from this section. Kind of.
Mm-hmm.
And so anyway, I'll just show you what they are.
Mm-hmm.
The slide is, well, it's one with a bunch of text on it. Anyway, you could look it up if you want. I mean, they mostly all say the same thing, but there's one that just summarizes it. So there's a thing called Bloch's theorem.
Mm-hmm.
Bloch is a German person. I don't believe he's still alive, but anyway, maybe he is. I don't know. Anyway, and basically the whole point is that we've been solving the Schrodinger equation, which I'm not going to write, but we've been solving it for potentials that just go to infinity. That basically, like, potentials that are only at one location. So like the square well or the square barrier or something like that. But what if you have a periodic one? This is actually much more sort of reasonable in terms of like doing something that's in real life, because materials like surfaces and metals and all that stuff have electrons that it's not just like, oh, there's a hydrogen atom in the universe and it's empty, like, which is what we've been doing.
Right.
This is like this is periodic with a period A, so the potential might look like, this or something. And it goes on forever. And in this case, the period, which is the distance between when it repeats, of course, would just be A for whatever. So this is a periodic potential. Obviously, this is a little bit of a silly one. This is like the one he uses in an example. It's kind of a simple one. It's called some Kronig-Penny model or something like that. But the more realistic one might be like a bunch of 1/r like atoms, like that. I mean, something, so it would just be basically a bunch of nuclei, and then the electrons would sometimes exist like in bound states around a few of them in like a crystal or something. But in like a metal, for example, we know that how metals work is the electrons are sort of exist along all of them. They're not like isolated. That's why they're conductors and all that stuff. So anyway, so these are both periodic potentials, but we're just going to use this fact for, like, we don't actually care what the V's look like. We just care that they're periodic like this. Then the solution to them, and of course we could go through all the differential equations, but the Bloch's theorem is just supposed to give us the answer really quickly, which is that the answer looks like e to the I kx, I'll explain what the k is in a second, times u of x, where u of x plus a is u of x. And all this means is that u is a periodic function with the same period. So all this means is that the solution to Schrodinger's equation, in other words, the wave function of a periodic potential, is some plane wave. So this is a plane wave, because remember, remember when we solve the Schrodinger equation in a vacuum, we get just e to the I kx or something. It's a plane wave with a wave number at k is what we called that. It's like the frequency in space, that kind of thing. So it's that times a periodic function. So, but this is not periodic. This is just its own thing. But then k labels all the possible states. So if you're talking about like some matter with some electrons moving around in it, and you want to say, well, all the electrons are like what are the possible states they could be in? They're labeled just by k. That's the only sort of parameter in this. So, yeah. And h bar k is called the crystal momentum. Is that how you spell crystal? Yeah, okay. I thought there was an H in there or something. Anyway, it's called the crystal momentum. It's also sometimes written as P for momentum. And we'll see that this relation matters because when you have this, I'm going to forget H. I believe that's correct. This is the uncertainty principle in one dimension. So this is just for any state, or any quantum state, or any wave function. The uncertainty in its position times the uncertainty in its momentum is greater than or equal to h. And so the sort of the limit of this, like the maximum value kind of thing, or the minimum value, whatever you call it, is equal to h. And this is going to come up for question, I think, number 2. So I go over the derivation a little bit in the last video, but this is essentially Heisenberg uncertainty principle. And the reason we need this is because later we're going to have like, okay, so remember when we had the energy states in a box? We just had like a 3-dimensional box, or a 1-dimensional box, I guess, but whatever. And we had those states that had like,
they were the shells.
Yeah, basically the shells where they were like values. Sometimes we had multiple in the same one.
Yeah.
Those were the possible states, and they were all separate. Right. And so it was kind of easy to do the quantum mechanics of that because everything was sort of distinct and separate. And the times when they weren't separate, they were exactly the same. Mm-hmm. In this case, well, I'll get to this in a second, but we're going to put states on here. But we're actually going to put states like, we're going to like shove them as close together as they can be. Great. So you might think, well, why can't I just like, it's kind of like saying, instead of, for this kind of potential, why can't I just, if each state has to have a different quantum number, that's the whole, well, sorry. We need this fact, and we need another quantum mechanics fact, which is the Pauli exclusion principle, which just says that electrons can't be in the same quantum state. Or another way of saying that for electrons is because we know electrons are spin 1/2. That just means that 2 electrons can fit in each energy state, because the full state involves the spin, and they're actually all in different states. Mm-hmm. So the statement is that no 2 fermions they're called fermions, but electrons are an example. This is the only example you're ever going to use anywhere. Is can't be in the same quantum state, and if each energy state involves 2 spins, then of course, basically you can think of it as just 2 electrons per energy state. Mm-hmm. But what if we have like a bunch of energy states? Like, and I keep just saying I will get to this. I just don't want to yet because I have to say something else first. But if we have like a whole band of states that you can like, you might think, why can't you just sort of pile them in? And if the states are labeled by k, and k is not like an integer, it's not like where we had n squared before, where n had to be integers. Our quantum number here is just a regular, it's a real number. So that seems like, well, then you could put infinitely many, right? Mm-hmm. Because you can just, any 2 real numbers you have, you can go halfway in between. Well, the uncertainty principle actually gives us a limit on the number of states we can have. And the reason is because if this is our limit for the uncertainty principle, delta x is the uncertainty in position. Well, delta x has to be, let's say at the limit, at the most uncertain in position of our wave function psi, can be a, the crystal period. And the reason for that is because if our uncertainty in a position is more than this, it sort of doesn't even make sense. Right. Like, it's not really in a period. It's like this is periodic. This requires us to have some sense of that a limit on the delta x. So therefore, the delta p, so this is the uncertainty, the momentum of our state, which we don't quite know what that means yet. Actually, we do. I wrote it, but we'll get to that. So a delta p is h. This is the limit for delta p's, and then if we therefore get delta p is h over a, and then delta p, I said p is actually h bar times k, and k is this value here. So we can write this as h bar delta k, and oh, actually, hold on, I'm missing it. I'm missing a 2 pi or something. So the point is here that h bar is 2 pi times h. Or no, sorry. H over, hold on. All right, I'm looking this up. H bar. H bar is, I think it's h over 2 pi, right?
So delta kx equals 2 pi over delta x. I don't know if that matters.
Delta k is 2. Yes, that's what I'm trying. Yes, so I'm trying to get that delta k is 2 pi over. Oh wait, that's supposed to be an a. Oh, okay. Then no, that's fine. That's fine. Okay, I'm fine.
Okay.
The thing that I need to do now is so the difference between h and h bar is just that h bar is 2 pi h. And therefore I can write 2 pi h here, delta k. That's equal to that.
Right.
And the h's cancel.
Mm,
Did I put the 2 pi? Oh, okay, sorry. So then it's h over 2 pi.
that's, yeah.
I'm an expert.
Of course.
So h over 2 pi. I'm sorry, it just didn't say on the first page of Wikipedia, so that's why.
So why?
It's, I mean, I wish they just used the same one everywhere. H bar is h over 2 pi. Okay, good. Okay, perfect.
We're golden.
Sorry. Now, why they use h bar in some places and h in other places, I mean, if you want a reason why there's a 2 pi anywhere in here, like why is pi in here? Like what circles, like what are the reason is because you have this e to the I k. K is defined as the thing that goes in here, and e to the I k is something we know is like sine, cosine.
Mm-hmm.
So that's why the k kind of comes with its own 2 pi in it. It comes with its own 2 pi. Sort of k divided by 2 pi would be sort of maybe more reasonable. It would be like instead of an angular spatial frequency, it would be like a total spatial frequency. Anyway, whatever, doesn't matter. So the point is that now this is equal to this, and we can cancel the h's, and we get that 2 pi over a is delta k. Now, what does this mean? Why did we kind of forgot why we did all this? The point of this is to say that if I'm going, and now I have to actually explain this. So this is called this diagram here is energy over k. So this is called, what is this called? The Brillouin zone. I don't know if that's how you spell it. I think that's how you spell it. Anyway, I don't know if they might mention the name in the book. Or he mentions it like once in his slideshow.
Mm-hmm.
It might be mentioned in the books. It doesn't really matter. It's just the E over K diagram.
Right.
and this seems like a weird thing to do because so far, whenever I've drawn anything for quantum mechanics, we've always drawn it as energy over space, right? So like E over K, well, what is this? Like that seems like such a weird abstract thing, and the answer is you're absolutely right. It's very weird and abstract, and it's very hard to visualize.
Read my mind.
So this is called this dimension here. So this is one dimensional because we only have an x. I put a vector here, but really we could have like a x, y, z, like a three-dimensional version, and then k would be a three-dimensional vector, right? It would be just a vector, but it would be point in 3 dimensions, and we'd have what this is called the reciprocal lattice. Reciprocal lattice is defined by k. So basically, the whole point of this is that because because the potential is periodic, therefore the wave function is periodic, therefore the states are only different by k. So it makes more sense to plot things in terms of k. So each sort of dot on here, if I put a dot right there, this represents a k value of less than pi over a and greater than 0. And therefore this represents, if I plug in that value of k, that's just a state. And it's still periodic in space, but it would be a little silly to draw like a wave function up and down. It would be hard to distinguish. This is like where the information is. So, and the reason I can't do between higher than pi over a or less than pi over a is because if I plug in like this is periodic. It's a plane wave.
Mm-hmm.
So if I write this as sines and cosines, of course, if you go beyond 2 pi, right, or in this case, it would be minus pi to pi. Of course, those functions are periodic. So this function is actually periodic itself, and therefore, I only need to draw between these two and actually get all the possible states here, right? The state that would be like a little past here is the same as this state,
Okay.
right? It's like, so, and there's I think in the book they do a little derivation where they plug that in. And so the Brillouin zone is just the zone between negative pi over a and pi over a, which are the limits on k. You could also pick 0 and 2 pi over a if you want. They just tend to pick this as by convention. But these are the values for k, such that every point on here, and I just drew these curves randomly, so don't worry about the curves. The point is that every point on here represents a single wave function. And so now our question, originally before we did this, our question was, why can't you just like pack all the states like as close together as you want? Why can't you have basically infinitely many states? Because you just make k, anytime you pick, you think you're full of k's, just take 2 and take the average, right?
Yeah,
and then if
right.
that's in there, take that. Like you can always do that. There's infinitely many real numbers.
Right.
There's an uncountable number of real numbers. Anyway, the reason we can't do that is because the uncertainty. This is the reason. The uncertainty in the k value has to be, and if we kept the greater than sign for the whole thing, this is like that, then the uncertainty in k would have to be greater than or equal to, so it's sort of backwards, but have to be greater than or equal to 2 pi over a. Which means if they're packed as close as they can be by the uncertainty principle, then this width between two adjacent dots would be 2 pi over a.
Okay.
Does that make sense? So in other words, we can't pack them as close as we want, because if we try to pack them closer and closer together by the uncertainty principle, this would become very small, and therefore this would become very large, and eventually it would become larger than our lattice, which means we don't really have states anymore.
Okay.
So this is called phase space. So the delta x times delta p is, you could think of that as a sort of a square of area in phase space. And question 2 on the homework asks you to essentially do what I just did in 3 dimensions. So all it is just, it's this times, so this is true, but if you have another copy where it's delta y, really I should have px everywhere, right? Because you could have more than one dimension, and this is kx, 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 But this is just one dimensional, this whole problem so far. And in the other video, I actually do it all out. So if you're having trouble, but you could, it's essentially, this is what I'm, this is the same thing. It's delta y, delta py is greater than h, and blah, blah, blah. And when you do them all together, you get the thing that's in his slides, which says that the phase space volume associated with a single state of a free particle is like 2 pi cubed, because, and somehow they do something with the a. Anyway, whatever. So 2 pi cubed you get.
Okay.
I think it should be 2 pi over. Maybe they're setting a to be 1 somehow.
Seems like there.
Anyway, this should be what you get, because obviously it wouldn't make sense for this to be 2 pi because that's the whole thing. So anyway, so that is. So in this case, this is the volume. This is the sort of the limit on how closely packed we can get our k's, and then using some. Now you might think, okay, let's count how many we can fit though, and forget about the fact that there's a curve. The reason there's a curve is because you can't give them any energies. There's some relation that comes from other stuff that we won't get into about the actual relationship between the k value and the energy. I don't remember if that's any of the questions, but I don't think it is. But anyway, so therefore you get some, but the point is that you can only fit them sort of horizontally like this. So we should be able to figure out if the range is 2 pi, we should be able to figure out how many states you can fit, and that's question number 3, I think. And they give you the answer essentially, n.
Per meter could fit in the lowest energy.
Yes, and they give you n. And I think it's 2 times 2 kf, which is the Fermi level, which I'll talk about in a second, over 2 pi, I think.
Yeah.
And this 2 pi makes sense because that's the range.
Right.
this kf over 2 pi would be the ratio of the, well, hold on, I'm talking about saying this 2 is because each dot I draw in here is actually 2 electrons because it's
Okay.
up and down. And the point is that you're supposed to just be taking this whole range and dividing it by how spaced you need the states to be,
Right.
and then counting them in one dimension. Now, of course, in many dimensions you get a different number, but somehow they get this, and they explain where the 2 comes from, and they explain where this comes from. They don't explain where this 2 comes from. That's I still don't know.
Okay.
But the point is just use it for that question. I think you just plug things in.
Great.
But the important anyway. These are not conceptually interesting problems to solve. I think.
Right.
I want to make sure that everyone understands the conceptually interesting parts, the parts that are not just figuring out where twos come from. I mean, sometimes those are important, like this, but here it's probably just some silly little thing, algebra thing. But the Fermi level, so I should say what K Fermi is. Well, I should say what E Fermi is. So E F, which is the Fermi energy. This is usually when they say Fermi level. I should have been more careful. Fermi level usually means Fermi energy, but not. This is the Fermi momentum, which is another thing. But this means that let's say I had this as my system. So your system, quote unquote, means that. Sorry. Let me erase some of this and then shift topics a little bit to start talking about this as its own quantum. This is the solution to the Schrodinger equation. These are called bands.
Mm-hmm.
This is the lowest band and the next band or whatever, right? And the point is that this is really what we care about with the actual solutions. Where can the electrons go? We know that they can fit or whatever, but where actually can they go? Like, if they have this K value, what energy must they have?
Mm-hmm.
That's actually we're not free to like give them any energy if we give them some momentum. They're fixed by this curve, which is the solution to the Schrodinger equation. That's what the whole, it's just that in this case it's sort of continuous instead of being those discrete levels that we've had for the other systems. So anyway, these are the solutions, and the solutions are called bands. And I mean, you could just think of it like an atom. Like if this is the nucleus of an atom, these are just the shells. But because it's continuous and because it has these weird properties, they're not all like shells, like distance shells. They're sort of distances. You can think of them as distances away from the surface of the material. And then you might have a bunch of bands and they have different curves and all that stuff. So what the Fermi energy is you have these bands and you have a bunch of electrons all in them because your material has electrons. But what if you just took all the electrons, no matter where they are, and just cooled them all down to what they say is to absolute zero, but that just means shove them into the lowest positions they can. So take your first electron, put it right at the lowest energy point,
Mm-hmm.
and then just fill them in like this until you've used all your electrons. Then, let's say this is the highest level you get to.
Okay.
Then this is EF. This is the Fermi energy.
Oh, okay.
So it doesn't have anything to do with the actual system. Like the system is the solution. The lines I drew are the solutions to the Schrodinger equation. Each electron point has to be on this curves, these bands.
Mm-hmm.
But the bands themselves just exist no matter what. It's just like how electron shells exist. Like hydrogen has a bunch of electron shells, but like there's almost never an electron in like the 7th energy level of a hydrogen atom.
No.
Right? But it's still there because it's the solution to the system. It's just not a state that's occupied.
Right.
So if you take all the occupied states and pack them into the lowest energy levels, the height that you get to, the height in energy space, which is the vertical direction here,
Mm-hmm.
is the Fermi energy.
Okay.
And now, why is the Fermi energy important? Well, it's sort of not when you're doing anything with like these when you're doing anything with wave functions. But the point is that if let's say you have a system, and sorry, I should have said this. These are bands, but this space is called a band gap, which is like, yeah, obviously it's a gap. But it actually is kind of weird because, I mean, it's not that weird, I guess. There is no state that you can be in with a with a energy level of like this much. Which I guess is not, the reason I say it's not that weird is because
Yeah.
that's what we've been doing the whole time. When you have the square well with those lines,
Mhm.
or a hydrogen atom, if you just pick halfway between two shells,
There's
you just
nothing
can't,
there.
yeah, you just can't have that energy. You
Right.
could drop down and lose a little bit of energy or whatever. But, so it's not that weird that you have these gaps.
Mhm.
But what's interesting about them is that because, okay, so let me draw this thing. So I'll draw a material. So this is going to be an actual material. And the reason I'm drawing the bands to be this shape is just because they do it in the book. I don't know, they don't offer an explanation of why things are like that. I don't know if that's common. I assume it's probably common, but I don't know much about it. But I'm just going to keep drawing them like that.
I'll take it.
So this is K and this is E. So let's say your material has, if you do find the Fermi energy, let's say this lower band is completely occupied, and then the higher band is a little bit occupied, like that. So your Fermi energy goes through a band. Oh. So I'll write E Fermi goes through a band. Meaning that your highest excited electron is midway through a band. It's not at the top, it's not, right? What does this mean for, like, who cares? Like, what does this mean about this material?
Right.
Where a band is full, that's fine, but the next one is such that, well, what if I just gave this a very, very, very tiny amount of energy? Or, I mean, well, the reason why they say that this is absolute zero is because thermal, like, if it's just a little bit of heat,
Mhm.
any amount of heat, causes electrons to jump around in states all the time. And the reason is because the energy, like the next state
Mhm.
is here. Actually, I should draw it as like a hole because there's nothing there yet.
Right.
So it's like an open hole. This is the next sort of next state. The energy difference between those two is very, very small. Obviously, I'm exaggerating, but it's like, it's really small. So even if it just has a little bit of heat, it'll just bubble up and down in all those energy levels. So, and so in this part, the part above the Fermi level,
Mhm.
or sorry, that's not true. The highest occupied band is called the conduction band.
Mhm.
So this is the conduction band. Because that's where electrons can freely move around. It's like a highway with nothing in the way. Right? This one, it would be kind of hard to shove, like it's occupied. But this one is the conduction band. But now what if you have a conduction band that's, if you have everything at the lowest level, that means that things can jump up to this high level into the conduction band very, very quickly and jump around through your whole material. So this object right here is a conductor. And I'll show you why it's a conductor. It'll make more sense when I show you what an insulator is. Because otherwise you're like, okay, well, so sure, everything's like that, but like, so an insulator has a Fermi level. Let's say this is your band, and let's say your Fermi level is like right here. So it's basically right above the top of a band or something like that. Or it's basically like this band is occupied, and this one up here is not. So your Fermi level is somehow between. I guess you can't really say it's here because there's no states there, but like it's basically here. Now, what does this mean to? So to excite an electron here, so this is now the conduction band, right? Because it's the one where there's mostly free things. Now to excite an electron, to get an electron into the conduction band, you have to give it that much energy. That's like a ton of energy you have to give it. So it tends, so even like thermal fluctuations or small amounts of energy, it's very difficult to get it from here to here. This is a large gap. This is a large gap between energies. So this is called an insulator.
That gap.
A system where these are the band structures.
Oh, okay.
And I mean, of course, the same material, I mean, a material just has a certain band structure. If you just take away some of its electrons, it could turn into one or the other, right? Because it just depends on how many electrons it has.
Oh, okay.
But obviously, most materials it's not really up to you how many electrons it has because it's just because of the atoms, right?
Right.
If it's like magnesium or like a metal,
Mm-hmm.
I don't know why I picked magnesium. It's just a metal. I mean, it has a few extra electrons in its outer layer, and so that's why it tends to be ionized really easily. Obviously, in chemistry, you know about that.
Mm-hmm.
But when it's in a surface,
Right.
that means that it's sort of this band actually could correspond to like the highest, the n equals what for magnesium it would be like n equals whatever 3 something.
Yeah.
And it has 2 electrons in it or something. Anyway, whatever.
It's been a while.
Something like that.
Yeah.
And the point is that because of that, it's basically like this. And the electrons, those few electrons, can very easily be excited. They only take like almost no, like this is like almost 0.
Mm-hmm.
This could be high or low, depending on the material, but it could be very high. It would be generally significantly higher than the distance between 2 states.
Right.
Because of course, as you see in the problems, when they ask how many states fit, it's like 10 to the 30. Like it's a ton of electrons can fit in each band.
Okay.
And so the distance between them is they're really, really, really tightly packed. I'm exaggerating that, but like this is not exaggerated. This is actually a significant distance.
Mm-hmm.
So if you had to overcome this to start conducting, that would be really difficult.
Yeah.
And then the third object that you could have would be, what if you had one where it was basically this, an insulator, but you had it so that because of the material properties, and this would just be you'd have to find a material that does this. It's not easy to like create it. Material where the band gap was like really small, right? And then the Fermi level was still sort of above the bottom one, and the bottom one, of course, is still occupied. Like, what if you just found a material where the gap was really small? Of course, it's not going to be quite. You're never going to get it as small as the between each of these things, but you could have it be sufficiently small that above maybe a reasonable room temperature or something,
Mm-hmm.
it actually gets they get excited enough to jump, and at below a certain temperature, they're not excited enough to jump.
Okay.
Right here, if I exaggerate this and make it like a pure insulator, this would be so huge that no matter how hot it gets, it's almost never going to like make this jump. But this could be really small so that maybe above a certain temperature, maybe when other things happen, we have a few more electrons that get in there, you can get things to jump. This is called a semiconductor.
Okay.
So a semiconductor. And again, this depends on the band structure. It doesn't depend on the electrons, because the electrons just fill in whatever they're going to fill in. This depends on the band structure, and which just depends on the material. So you have to this is things you have to look up. Like, what's the gap between the valence band or conductor? This is called the valence, sometimes also called the valence band, I should say.
Oh, I know.
Valence band, yes, I'm sure you do.
Valence electrons.
Yes. So, or a conduction band, and the last filled one doesn't really matter. There could be many more filled bands. Doesn't really matter. As you know,
It's-
only the valence electrons
It's
participate
the
in
only ones
things.
that matter.
Exactly.
Yeah. So you just kind of answered my question, don't worry.
That's, okay. Well, I was just gonna say this is like silicon.
Yeah.
That's why silicon's used, is because silicon. It's not like you can't make. I mean, I guess you could make materials like this.
Mm-hmm.
It's generally really hard. It just happens to be that silicon is an element where the gap between, and it has 4 valence electrons, so it's kind of halfway. It's not clearly a.
It's the outermost filled shell, and the next one that's not filled at all.
Yes.
Okay.
Yes. The lower one I'm drawing in all these is the
The
outermost filled shell. Yes.
Okay.
And the top one is the one that's not filled.
Okay. That makes sense.
And so the farther you get toward the non-metals, to the right,
To noble gases.
to noble gases, you would have basically the lowest non-filled one would have nothing in it, and they don't conduct electricity at all, basically, because
They're happy.
because they're happy, and so therefore because the gap between it is very large.
Right.
For whatever reason, I'm not totally sure why silicon has this gap. I mean, I know, of course, it does have. I'm not drawing it to scale, but
Mhm.
4 electron. Well, this is for a material of silicon, not for a single atom, but it does have 4 electrons, so it's kind of could go either way, I guess. But anyway, I've gone beyond the things I know
I
about.
need to look at periodic table.
Yeah. So anyway, the point is that these 3 a semiconductor, an insulator, and a conductor, those he wants you to know that's what they look like.
Okay.
But the difference between them is that the band gap is the thing that matters, and where the Fermi level is
Mm-hmm.
in relation to the bands.
Right. So the insulator and the semiconductors are the band gaps, but the conductor is the gaps between electrons.
Yes, and so I would say to excite an electron in a conductor, you only need to cross from absolute zero.
Right.
You only need to give it enough energy between states in the same band, which is very small.
Okay.
Whereas to excite an electron from an insulator, you need to cross a large gap, and to excite an electron in a semiconductor, you need to cross a very small gap.
Okay. So it's like going from like the S shell to the P shell.
Yeah, right.
In
Exactly.
terms of going from like 2p to 3p.
Exactly. Yeah. So if you had to go from if you had to make an electron go from 3p to 3d or whatever,
Mm-hmm.
that I think. Okay, I don't know what I'm talking about anymore, but
but
I think that would be easier
it would.
than going from 3 to 4
Like-
of anything.
Yeah, like 4s.
Yeah, so this would be like 3 and 4, and so you could do it. You just need to like really try.
A lot of energy.
This could happen by accident,
Right.
just from shuffling
Going
around
from,
because
like,
of thermal.
3p to 3d.
Right, and this might I've lost the analogy, but this is something where it still has to cross a gap. It's just that the gap happens to be very, very small.
Okay.
And this is of course very rare because most materials have large gaps.
Right.
It just happens to be that some of them have a very small one.
Okay. Cool.
Yeah. That was everything on that slide. Yeah. Okay. Okay, so what else do you want to talk about? So this is like basically a summary of the other one. I would watch the other one obviously
I
still
will.
because I do literally give you hints for the homework.
Love
like
that.
explicit, the homework at the end of the book I know is like there's a lot of like E equals PC type questions like for photons.
For the actual questions in the book, not like the
The ones at the end of the chapter.
right.
For
okay.
for those ones, there's a lot of photon questions where, and you have the thing with like hc over lambda or whatever.
Mhm.
So those are like the types of, so those are things we've done before, and they're not super. The ones within the chapter are a little more difficult because
Odd.
I don't know, they just are. So anyway, but I give hints for all of them except for
Mhm.
number 6, which is the very last question. I just say it's a
Extra
bonus
credit. Okay.
because I don't know how to do it.
For 1.1, the question where it's like the last part of the question, does the answer depend on which band the electron is for the
Oh, yes,
wavelength?
you were talking about that before. Yeah, so in that case, the bands are like these, and we can kind of see that, no, this is actually K space, so this is not real space,
Right.
but all the bands
Have
are
the
just
same-
different values of K. The wave functions are actually multiplied by the same periodic function.
Okay.
So the bands actually have all the same period.
Okay.
So none of the wavelengths depend on the band level.
Okay. That makes sense. Let me write
Yeah, that's a tricky one because it seems like the answer is probably.
that down.
And I believe the first part you have to use this fact. Or I guess the other way around. Lambda is 2 pi over k. I mean, they're the same equation, of course, but
Mhm.
you have to solve for lambda. And when they say when k equals 0, well, what do you get for the? So the first part of the question is when is tells you k equals 0, right?
Right.
And it says what's the wavelength? Well, of course we could plug it in. We get lambda equals 2 pi over k, and then it would be undefined.
Yeah.
So that seems weird. Now, usually when you divide by 0, the answer is infinity
Mhm.
in physics. You should not say that in a math context, because that's not whatever. Usually it's infinity.
Mhm.
But let's try to understand that a little better. Well, that means that the wave function with the actual and of course when we talk about these band stuff, almost no one even ever talks about the wave function. But that's really what it's all about, because the wave function is the thing that comes from Schrödinger's equation, which is the whole governing thing. if k equals 0 here, this is just 1, and we just get this periodic function with no plane wave here. So it's kind of like saying the solutions look like some kind of periodic thing times a plane wave. What's the wavelength of that plane wave? Well, we didn't have a plane wave. So I guess you could say it's like constant, therefore the wavelength is like infinity. Right? Like a flat function is like a wave with a wavelength of infinity.
Okay.
That's just the argument you could use to explain why that's true. But that is the answer. The answer is for k equals 0, the wavelength is infinity. And then the second part asks if k is, pi over a, of course, and you can just plug in pi over a to that, and you get 2 over a or whatever it is. Or a over 2, maybe, I don't know, whatever.
Okay. Okay. Yeah.
I guess you get a over 2. Yeah, I guess you get a over... Or no, you get 2a. I'm sorry. You get 2a, and... Why do you get wavelength as 2a? That's kind of weird.
Yeah.
Wavelength is... Do you think it would just be a? Because that's the... you should have the... I don't know. Anyway, that is... According to the answers, that is true. It's 2a. But I'm not totally sure why there's a 2. Maybe it's related to why this 2 is here, which I also don't understand. Whatever. Oh, sorry, I should say k Fermi is just the k value of the highest electron, which I don't think comes up that often. It's just in there, but...
No, I know, that makes sense, because then you divide by pi and multiply by a.
Yes. Okay, there we go. It does make sense.
I just had
We
to write it
figured it out.
down. Okay. Hang on, let me-
Yeah. So yeah.
We got there. It's fine. Sweet.
And then for a couple of the questions at the end of the chapter, they ask you about values for different materials,
Yeah.
and I don't
There's
know.
a whole list of them.
There's a whole list of them, and I actually don't know if you're supposed to look them up. I assume you are.
I
'cause
can't
you
imagine I'd know this off the top of my head.
But I don't. Is it in the book somewhere? Like I didn't see it anywhere in the. I mean, I didn't really look very hard, but I didn't see it clearly. It's not like I don't know. Hopefully, it's somewhere in the chapter, or you could of course just look it up online.
I think that's what I'm going to do. Oh, wait.
Oh, that
Oh,
looks
no.
like a table.
It does look like a table. Effective mass parameters of semiconductors.
Oh no, it's not mass. So mass parameters are something more complicated.
Yeah, that didn't look right.
Yeah, which I am not qualified to talk about right now. If they
Gotta
come
do
up in
some
the homework.
research.
I vaguely know what they are.
Well, there's no table in here,
Okay,
which is great.
so I guess you're supposed to look it up.
Okay.
This homework I'm going to be a lot less interested in
Oh, okay.
every problem. Because I essentially think that according to so basically this is always the problem with this, not the problem I should say, but the thing with this class is that his slides, I think, emphasize what he wants you to know.
Mm-hmm.
And the book and the problems emphasize things that are more complicated sometimes and not quite as relevant. And so based on his slides, everything I just said to you, I think is what he wants you to know.
Mm-hmm.
So some of the questions I'm like, well, I would have to do a bunch of work to like write out my answers to this. And luckily I don't have to because he puts the answers for me to see, which I will put for you guys to see. But I don't think that that's super helpful. So I'm hoping that if you just understand this and just try something with the homeworks, and I just take it easy with the grading on the homeworks, obviously, then on the quizzes, which is sort of really what matters, that because you remember this stuff, you'll all do a great job.
Love that.
That's my sort of plan.
Okay. So 2, you just use the E equals HC and then plug it into the E equals PC.
Yes, I don't quite remember what the problem is, but I believe it's like...
2 is like, what's the momentum of visible light with this wavelength? What's the wavelength of the photon?
Oh, yes.
Would have a momentum corresponding to the momentum of an electron at the first zone edge, and he gives this really complicated equation.
Okay. Then yes.
Okay.
Yes, in that case, photons just have this. I think it's just because we haven't explicitly said this before, but this is true for photons.
Okay.
I should say
For photons.
photons, and p is the momentum. So I don't think we've explicitly said what the momentum of a photon is, but it's actually maybe we did because it's just this, but if you use h over lambda equals p, oh we did, because remember this is the de Broglie wavelength
Oh, boy.
was h over p.
Yeah.
De Broglie. It's not how you pronounce it, but whatever. He was French, so
I'm
whatever,
not
who cares?
French,
Uh,
even remotely.
Yeah. So I'm not either. I'm 60% Irish.
A name like
Just so you
Keegan,
know.
I
Yes,
would
indeed.
have guessed.
Yeah. Okay, that agrees with this. Okay, let's make sure. Yeah. So because of the de Broglie thing that tells you the wavelength, which is h over p, which remember there was a question that was like a baseball has a velocity of this. What's its de Broglie wavelength? And you had to do h over the momentum mv.
Yeah.
Of course, that's like a silly little. You'd never really do that, but that's interesting. So using this and this, we can plug in for here and get the
Okay.
momentum of a photon. It's of course by momentum, you can't say that it's equal to mv
Right.
because for a photon, it's always traveling at the speed of light and it has no mass.
Right.
So that wouldn't really make sense for this. But there is a thing called the momentum of a photon, which is that.
Okay. And then, so what energy? Wouldn't you have already found the energy, and then it's asking for it again?
Yeah, if they tell, well, say they say visible, right?
Yeah.
So I think you just pick the wavelength of a visible photon.
So it's 500.
Oh, okay. They tell you this.
Mhm.
These are constants. You find energy,
Right.
and then you can just divide by c to get.
P.
Or you don't.
Yeah, but like number 2 asks you to do that, and then number 3 asks for the energy. So is it already
Oh.
asking for a number you got?
Yeah, I guess technically you could do it with technically you could do
that
this
for number 2.
without the energy. Yeah.
Okay. I think that's what I was wondering.
I think that's what they were probably thinking
It
when they
seemed
wrote
like
the
a
question.
very roundabout way.
Yeah, sorry. You should not memorize this. You should not memorize these 3 equations because only pick any two, and you'll have everything.
Sweet.
It's like one of those. It's like an overdetermined system.
Okay. Okay. And then so 11.2, which is the one with not zillion. It's just in 3 dimensions. So it looks
Oh,
like a
that's
lot.
the delta x delta.
Looks like a lot to me.
Yeah, they want to show that this is 2 pi. Now I know that they do it in 3 dimensions and everything's cubed, but this is isn't that what it says? Like this times delta
Yeah, it
y
gives
delta k.
V of 2 pi cubed.
Yes. So okay, good. So they're so it's showing that this is true,
Yeah.
but then multiply this side by.
Well, just multiply them all together in order to get.
Yes, exactly. So
volume.
each one separately comes from
Like length times width times.
delta x delta p
Right.
is h, and then delta p is related to delta k through h bar, and h bar is related to h through 2 pi. So then you also have to use. So I could even write this as h over 2 pi,
Mm-hmm.
and then you'll see that of course everything cancels except for 2 pi.
Mm-hmm.
And when I did it before, I filled in delta x equals a, but of course, the problem doesn't want you to fill in delta x, so don't fill that in.
Okay.
But essentially, it's this. Just obviously put deltas here. This doesn't have a delta, of course, so it's just delta k
Mm-hmm.
is delta p, and then plug that into the uncertainty principle, and then you'll get this for
Okay.
1 dimension, and then of course they all just apply to all the dimensions. So
Okay.
you could even start with the uncertainty principle in 3 dimensions, which is this times the y version times the z version is h cubed. That's also
Okay.
places
That's
you can
that's
start.
what they give you.
Okay, good. Oh, okay, then there you go.
Mm-hmm.
So that's the whole thing. And the whole point of that is to show you the volume. They call it the volume of phase space, which just means that's just another way of saying how much space. Well, you'd have to draw a different diagram for like k versus x or something, but it would basically be how much. Based on the uncertainty principle, there's a smallest sort of space that something has to take up in x versus momentum space,
Mm-hmm.
which is sort of a really convoluted sentence, but
Sorry, I'm writing. So.
no. I'm gonna have a cough drop.
Nice.
Yeah.
Just wrote that twice. Lovely. Okay. So can I just show it for X and then just say same across 3
Yeah.
dimensions? Okay.
Yes.
Because that's what I want to do. I don't really want to write that out.
Yeah, you could probably actually just do this entire problem and literally conclude this, and then literally just say by symmetry,
Okay.
the three-dimensional version is this cubed, and therefore it's 2 pi cubed.
Mm-hmm. Okay. Yeah. So,
And the problem, of course, they're setting it up like you're not going to do that, but I don't see why you couldn't do that.
yeah. I'm just. That was my plan.
Sounds good to me.
Okay.
And then number 3 in the book was also a little confusing to me. I didn't totally know what they meant.
Is that the one with the extra 2 that you don't know what that
It has the extra 2, but even that. Well, anyway, just try your best.
Thanks.
I
Wow.
still don't totally understand.
What do you mean by that?
At some point before the quiz, obviously, but
Yeah.
after this is due, he'll tell me to post the solutions.
Okay.
And the solutions I didn't write.
Right. Do they not make sense with this?
Well, they might make sense, but I don't totally understand what the person who wrote them was thinking. And so,
Love that.
anyway, it'll be fine.
Okay.
I'll come up with some explanation for that.
So this one, fill this in. How many? Oh wait. Okay. So the equation to find out how many electrons per meter.
Oh, well, if this is the number of electrons n
Mm-hmm.
in this level, then the electrons per meter would be n over a, right?
Oh, okay.
I think that's just it. NL, I guess they call it. And then
They don't give you n. I guess n is.
N is, I think you have to fill it in, and they give you the K. They say like near the edge of the zone or something.
It says for a one-dimensional system with A equals 0.5 nanometers, how many electrons per meter could fit in the lowest energy band? Oh, an 11.5. Never mind. I just
Okay.
didn't look at the.
So I think they're saying KF is going to be pi over A because they're saying the whole band, so the whole band is filled. Therefore, KF, which is the highest value of this, is pi over A. So KF is pi over A. Maybe that's where the 2 comes from because that's only this half, and so there's actually
two
twice as
KFs.
many?
That's what it looks
Yeah.
like.
Okay. Oh, there we go. That's
Hey.
probably it.
I helped you solve
There
something.
you go. Thank you very much.
The
So that-
biologist out here.
wow. You should grade the homework.
Gladly.
So okay, that's reasonable. So therefore, that's just because of the definition of KF, I guess. And that's because the definition of that 0 was in the middle. It's kind of symmetric or something. But anyway, yeah, okay, that's reasonable. So 2K is the full sort of like I should say both sides of the Brillouin zone.
Mm-hmm.
And then you divide it by 2 pi, of course, to get the number of actual like regions you can have, and then times 2 because each one has 2 states, and it's the total number. And if you divide it by A, you'll get this. And so that's why. Will it depend on A? I guess it will. Yeah, it will depend on A, which is fine because they give you A.
Right.
I was just thinking somehow the A's were going to
So-
cancel, but they don't. Because you plug that in and
So
then
you
divide the
just-
whole thing by A.
You just do
You just do it, and it's just some
2
number.
times pi over A equals NL over A.
Um,
That doesn't make
so you would just do that. And I guess these cancel. And then KF is just pi over A, I guess.
Damn. Alright. All right. I think that answers my questions. At least for all of them. So the longest wavelength. Oh, band to band. Oh, so you have to find the longest thing that'll get it to jump the gap.
Yeah, so if you know the energy of the gap, the longest wavelength would actually be the smallest energy, right?
Mm-hmm.
Because it's in the denominator. So the longest lambda is lowest E. Therefore, if you once you find the smallest energy gap, so I guess you have to like do it for a bunch of them or like look through the you have to look something up and basically look for the smallest energy gap, right?
Okay.
And the smallest energy gap will give you by this relation. Just plug it in, you'll get the longest wavelength, and you can write down what the wavelength is and see if it's whatever visible light or something.
Okay. So just look for the smallest energy gap for all 7 of these.
Right, and the whole the physics part, which obviously you already know this, but I'll just say it again. The physics part is just that an electron going from one state to another state across any gap
Mm-hmm.
emits a photon with the energy of that, because energy is
Yeah.
conserved.
Right.
That's the physics. Of course, obviously that's like implicit in all this, but the fact that energy is conserved gives you the fact that why are we talking about photons in any of this? Photons can't be in any of these states,
right?
Because they can't have no momentum or anything like that. But the point is that whenever electrons move around between gaps or between states at all, some photon is emitted.
I'm trying to figure out how to Google that. Okay, well, I'm sure I can find something.
Maybe look up band gaps, silicon. I don't know, or like whatever the metals, magnesium, whatever they are.
Oh yeah, it's like, oh gosh, these names. There's gallium, silicon dioxide, aluminum oxide.
Oh, geez.
Yeah.
It's got to be like somewhere in the book, like in the back or
town.
somewhere.
You'd think, right?
Like, I don't know what you're supposed to.
Yeah, germanium. I kind of doubt that he has tables back here, and I'm right. Yeah, he doesn't have like a table of energy gaps
Yeah.
or band gaps.
Maybe just, I guess look up band gaps. I mean, there probably should be only one listed because, of course, there's a bunch of bands for each.
Yeah.
Probably infinitely many for every material, but there's only one that matters because that's the one between the valence band and the.
I'm assuming these are common ones. Hopefully there's
Yeah, they better be.
in here. Okay.
Obviously, if you can't find one, just don't do it. It's fine.
Couldn't find it, sorry.
If I see that like several people are not doing one of them, I'll be like, well, that's fine because it must be hard to find. But obviously, the only point of this, the only physics point of this, the only thing I'm looking for when I'm grading, in other words, is that you understand that to go between a gap requires a certain amount of energy, and so raising or lowering either absorbs or emits a photon with that exact energy, and therefore, because it has a photon with a certain energy, we can calculate the wavelength, and so.
So kind of looking and seeing which ones of these are good, like semiconductors, insulators.
Sure, if it requires a very small amount of energy, I mean, how do you know what's small? Because they're all going to be like 10 to the minus whatever. But if you'll see that like there's a visible light one, that might be interesting.
Mm-hmm.
Or like or I guess you could go the other way and be like, given a visible light photon shining on a metal, which ones will cause it to conduct electricity? Right? Will cause it to like. So that's where you'd look for an insulator basically, or a semiconductor where the gap has an energy where the lambda is 500 nanometers, whatever it is. So,
okay.
I don't know what you do with that information.
You know,
I'm not a physicist either, but not yet.
You'll get there.
Cross my fingers. I'm not an engineer, so I don't know what to do with any of this information.
Hey, me either.
But hopefully, one day
you'll be an engineer and
you
you
will
can
be.
solve
We'll all be
these.
engineers.
All right, awesome. That's all the questions I have.
Okay.
Thanks. I'll let you go.
Good, because this is one of the things. All right, I'll stop the video. But